Hello and welcome to Algebra. Today we're going to be looking at some special cases, some particular squares that are, we have perfect squares on either end of the perfect square trinomial, or we have the difference of two squares. We're going to be looking at some very special cases. Now these are the special cases that we're going to deal with. In every single one of these you have a perfect square as the leading term and a perfect square as the last term, the coefficient. Or it could be with two variables. There could be a separate variable there. But you have to have a perfect square in the front and you have to have a perfect square at the end. These two you could just factor normally. It's a nice shortcut. It will work, but you don't have to have those. This one is the most important of the bunch. It's called the difference of two squares. It is very, very important. So make sure that you know the difference of two squares. Well, if you break that down, it's difference, subtraction. You've got a perfect square in the front, perfect square at the end, so there's two squares, and you're taking the difference. So difference of two squares. It's going to be very important. Sometimes when you go through, if you have a binomial, at this point we haven't learned the discriminant. We don't know the quadratic formula. So the best that we can do is just look at it. If we see subtraction, we see a perfect square at the beginning and at the end, then we know we have the difference of two squares, and we've got to factor that out. So let's look at a few. What's a factored form of x squared minus 12x plus 36? Well, the first thing I'm going to check, is there a GCF? Is there something in common? We have an x, 2, 3, 2, 3. No, there's nothing in common. So is this a perfect square? Yes, it's x squared. Is this a perfect square? Yeah, 6 squared. Now we learned a little saying when we were doing the FOIL special cases. First one squared, last one squared, multiply and double. If you go back here, let's say we're going this way. First one squared, last one squared, multiply a times b, and double. It works with this case. So you can kind of work backwards too. Do you have first one squared, last one squared, multiply these together, 6x, and double it? Yes, you get 12. So this is an example of a perfect square trinomial. So it's going to be x and a 6, and x and a 6. And what is the sign? It's a negative. X minus 6, x minus 6. Like I told you earlier, because this is a trinomial, you can use the box method. So just to double check, let's use the box method. 36 is 2 times 18. 18 is 2 times 9. 9 is 3 times 3. So we have 2 times 2 times 3 times 3. Do we see the same or different sign? It's going to be the same sign. Do we add or subtract them? Since it's addition, we're going to add the factors. Well, don't forget the obvious one, 1 and 36. 2 works, 2 and 9 times 2, 18. 3 works, 3 and 2 times 2, 4 times 3, 12. 4, I do see 2 2's, 4 times 9. 5, don't see a 5. 6, yes, 2 times 3 is 6 times 6. And then I'm back up the next column, 6 is itself. So I want something that adds to give me 12. Well, these two add to give me 12. Should they be positive or negative? They should be negative to add together. Negative 6 plus negative 6 will give me the negative 12. So these two go in the corners with an x on them. And the x squared goes in top left. The 36 goes in the bottom right. This sign goes here. This sign goes here. There's an x in common and a 6. An x in common and a 6. So you see, you're going to come up with the same. It's just much quicker if you happen to remember the shortcut. It's not absolutely necessary, but it's a nice shortcut. Now, this is a binomial. When you see a binomial, up to this point, we don't have the quadratic formula. We'll learn that later. So we really need to have something that we can use with this. Well, the first one, is it a perfect square? Yes, it is. What times itself gives you z squared? Well, z does. So z squared. I'm going to rewrite it this way so that it's easier for the next step. What times itself gives me 9? Well, 3 times 3 gives me 9. So I'm going to rewrite it this way. Do I have to rewrite it that way? No, but it's going to be much more helpful in the next stage. This is z squared minus 3 squared. If you look back at a reference sheet, when you have something squared minus something squared, the first one plus the second one, the first one minus the second one. So this is going to be z plus 3, z minus 3. That's my answer. I do want to go back and double check. First, z squared, outside minus 3z, inside plus 3z, last minus 9. Well, 3z minus 3z is 0, so I have z squared minus 9, and that does check out. What is the factor form of this one? Well, is the first one a perfect square? Well, the first thing I need to check, actually, is to see if there's a GCF. Is there any number in common with 16x squared and 81? And the answer is no. If you can't see that very well, break it down to prime factors. 2 times 8, 8 is 2 times 4, 4 is 2 times 2. 81, 2 doesn't go into it, 3 does. 3 times 27, 27 is 3 times 9, 9 is 3 times 3. So is there anything in common with these? Absolutely not. So 16x squared, what times itself gives you 16x squared? Well, 4x times 4x gives you 16x squared. What times itself gives you 81? 9 times 9 gives you 81. And now I just split it up. This is the difference of two perfect squares. 4x plus 9, 4x minus 9. And we want to double check it. First, outside, inside, last. These subtract away to 0. Yes, this does work. Okay, as always, I want to see, is there a GCF? See, 24 is 2 times 12. 12 is 2 times 6. 6 is 2 times 3. 6 is 2 times 3. And you notice, this time there is a GCF. Now, if you don't pull that GCF, there's going to be no way to factor this. There's going to be no way to solve, it's going to be simplify at all until we get the discriminant. And we're going to learn that a little bit later. So we need to pull out this GCF. Well, I see that 2 and 3 are in common. So I'm going to pull that out front. 2 times 3 is 6. And then I'm just going to write the leftovers. 2 times 2 is 4. That's left over. That's not what I pulled out. And of course we have the g squared. Over here, nothing's left. So I just say minus 1. You can always put a 1 in there because this could be 2 times 3 times 1. Now I have something that I can work with. My only concern is, you know what, when we get that final answer, it's going to be very easy to forget that there was a 6 there. So I'm going to go ahead and write sort of the expanded version so that I remind myself, hey, you know, the answer is going to have a 6 in there somewhere. And that way the 6 will be out front. 4g squared minus 1, what times itself gives you 4g squared? Well, 2g does. So 2g squared minus 1 squared. Don't forget the 6. And at this point, 2g plus 1, 2g minus 1. We believe that's our answer, but again, let's double check. First, I'm going to FOIL these. 4g squared minus 2g plus 2g minus 1. Well, 2g minus 2g, that's 0. Now we just distribute this 6 onto both of these. 24g squared minus 6, and that does work. So the first thing you need to do when you see one of these, see if there's a GCF. If it's hard for you to see that, just break it down into its prime factors. And once you've done that, once you've looked to see if there's a GCF, you want to look to see is the first and the last term a perfect square. If it is, there may be a nice shortcut that you can use. If not, you You may want to try the box method if it's a trinomial. If it's a binomial and the difference of two squares will not work and there's no GCF, it is in simplified form. There'd be nothing else you could do. That'll do it for today. Have a good day.